Hi everyone, this video is on exercise 9i question 6, which is about the curve that has the equation y is equal to x times e to the power of x. And in part A, we want to find the exact coordinates of the stationary point on C and determine its nature. So it's similar to question 5, at least the first two parts are similar to the previous question. So if you have watched that video, you probably should have some idea at least. So we have y is equal to x times e to the x, and in order to find a stationary point, we first need to find the first derivative. So dy dx is equal to, we use the product rule because we have x and e to the x. So the first function times the derivative of the second function, e to the x just differentiates to e to the x, plus the first function differentiated, which is 1, times e to the x, which is going to be e to the x. And in order to find a stationary point, we set this equal to 0, the first derivative, and solve this equation. So we can take a factor of e to the x. So we are going to have e to the x times x plus 1 is equal to 0. Now we need to solve this equation. Either e to the x is equal to 0 or x plus 1 is equal to 0 for this equation to hold. But for the first part, e to the x can't be 0 because e to the x will never be 0. So this one doesn't have any solutions, whereas x plus 1 is equal to 0 indeed has a solution. So the solution is minus 1. Now minus 1 is the x coordinate of the stationary point. So that means we need to substitute minus 1 into the main equation, which is y is equal to x e to the x, in order to find the y coordinate. So when x is equal to minus 1, y is equal to minus 1 times e to the power of minus 1, or we can write this as minus 1 over e. So this is basically the answer to part A. So the stationary point has the coordinates minus 1, minus 1, e to the power of minus 1. So this is the answer to part A. Now in part B, we need to find the coordinates of any non-stationary points of inflection on C. So the question might sound a bit confusing, but it just means that find the points of inflection and choose the one that is not the stationary point. So that's what it's basically asking. So let's find the point of inflection first. And in order to do so, we need to find a second derivative. So for part B, the squared y by dx squared is equal to, we are going to differentiate this, which is, the first derivative. So we need another product rule. X, again, x times the derivative of e to the x, which is e to the x, then derivative of x, which is 1 times e to the x, plus this e to the x differentiated, which is again e to the x. And we can simplify this and then factorize x times e to the x plus 2e to the x. Then we can take a factor of e to the x, which is going to be x plus 2. And in order to find the points of inflection, we need to set this equal to 0. So we are going to again have two equations, either e to the x is equal to 0 or x plus 2 is equal to 0. And as we discussed, e to the x can't be 0, so that doesn't have any solutions. But this one has a solution, and that's minus 2. So x is equal to minus 2. And what we do at this state is that we need to go and find, basically see if it's indeed a point of inflection. Because remember, in order to do so, we need to check something, right? And that is checking that if what happens just before and after the x value that we found. So what I mean is that we are going to find, basically substitute the values of x is equal to, one of them is basically minus 2 plus 0.1, and then we substitute this into the equation of sub x is equal to minus 2 plus 0.1 into the equation of d squared y dx squared. That's the first test. And the second one is x is equal to minus 0.1 into the equation of dx squared by dx squared again. So again, this is just testing, right? We just want to know what's the behavior of the function just before and after the point of inflection that we found. So that's why I just added and subtracted a very small amount. You can go further and just add 10 and subtract 10. If it's a point of inflection, then it doesn't make a difference here, unless there are some certain conditions and limitations that you have with the function that you are given. So that's why it's probably safer to just stick with the small values. Okay, in this case, it's all about substituting these values and just find basically the sign of dx squared by dx squared. So you don't even need to write down the exact value. You can if you like, but the sign of them is very important. So we want to know which one gives us a negative sign, which one a positive sign. Right. So when we have minus 2 plus 0.1, we are going to get a positive value. And when we have minus 2 minus 0.1, we get a negative value. So this is exactly what we wanted to show, that this is a point of inflection, because at least the non-stationary point of inflection, because there is change of sign. So that's always what we want to get, because if we get two similar signs, then that means this is not the point of inflection. So hence, it's a point of inflection. Now, in order to find a point, we need to substitute, remember that, minus 2 into the equation of y is equal to x times e to the x to just get the y coordinate of the point of inflection. And by simply substituting that, we are going to get minus 2 times e to the power minus 2. So that's our point of that's the y coordinate of the point of inflection. So just to quickly write that down, when x is equal to minus 2, y is equal to minus 2 times e to the power minus 2. Hence, minus 2 e to the minus 2 is a point of inflection. So remember, the aim here was that to find the coordinates of any non-stationary points of inflection. And remember that x is equal to minus 2 is not the stationary point. Before I move on to part C, let me remind you that part A had actually two parts. So the first part was finding the exact coordinates of the stationary point on C, which I did, and that was minus 1 e to the minus 1. And it has also a second part which says, and determine its nature. So I didn't do that when I was doing part A because I needed the second derivative. So I kind of waited to find a second derivative from part B and then go back to that. So because in order to determine the nature of a stationary point, all we need to do is basically substituting the x value of the point of stationary into the second derivative equation. And then if we get a negative value, then that means that point has a maximum. But if it's positive, then that point has a minimum. So in this case, I'm going to write with a different color. So when x is equal to minus 1, d squared y dx squared is equal to, so all we need to do is just substituting that here. And so we are going to have e to the power minus 1 times, so minus 1 plus 2 is just 1, which is 1 over e, and 1 over e is positive. Hence, this is a minimum. So it's a minimum. Its nature is a minimum. And this is going to be very important for part C. Right, so far, just to quickly summarize, we have found the coordinates of the point of the stationary point, which is minus 1 and then minus 1 e to the minus 1. And also we show that it's a minimum. Then we found the other point of inflection that is non-stationary, and that has coordinates minus 2 e to the minus 2. So here. And now by using all of these and some of the maths that we know, we are going to answer part C, which says, hence sketch the graph of y is equal to x times e to the x. Right, for part C. So we want to sketch y is equal to x times e to the x. And it's a very interesting one because normally we usually, in questions, they're mostly about just solving questions analytically and more about just, using differentiation and other techniques. So, but this time we have a sketching and it's a very good practice. So the first thing that you should note here is that whenever you want to sketch, it's absolutely crucial to analyze the behavior of the curve at the extreme points. So what I mean is that you need to examine the behavior of the curve when when x tends to infinity, positive infinity, and also negative infinity. So those are very helpful for us. And then the second thing is obviously checking at 0. It's another crucial point. And another part which doesn't apply to this question is checking the asymptotes. But again, this doesn't apply here, so it's all right. And we have a sort of asymptote here, but not in the usual sense that we have, for example, in the reciprocal graphs or other types of graphs. And also another crucial part that we also need to take into consideration is using the stationary point and even point of inflection. And that's exactly the purpose of this question, that we found those 2 points in the previous parts, and now we want to use them. Okay, so starting with the easier more straightforward facts. When x is equal to 0, what's going to happen is that y is also going to be 0. So we know that the origin is part of the graph. That's the first one. Now the second thing that we can do is that we can just plot the points of the stationary point and the inflection point. So the stationary point has coordinates -1 over e to the -1. So that's somewhere roughly here. This is the stationary point. And the point of inflection has coordinates -2 to the power -2. So that's sort of here, slightly lower, at a lower position. Sorry, it's actually higher. Yeah, because -2 times e to the -2. Yeah, I was confused for a second, because this one -2 times e to the -2 is actually greater in terms of its negative value. So that's why the stationary point is at a lower position. So yeah, let's go like this, and then the point of inflection is slightly higher. So that's what we have so far. So we have found 3 points. This is the stationary point. We can even write the coordinates if it might be helpful. So -1, then -1, e to the -1. So -1 e to the power -1, and then the point of inflection is -2 e to the power -2. I also need to write the -2 that it has. So okay, now we have the points. The next step is analyzing the behavior of the function at extreme values. So let's see what happens as x tends to infinity, positive infinity. So as x tends to positive infinity, what's going to happen here is that if you just imagine, if the value of x gets extremely large and also e to the x extremely large, then the result is going to be a very, very big positive number. So that means from the positive side of the graph, as x tends to infinity, y also tends to infinity, right? Y tends to infinity as x tends to infinity. So the graph just keeps going up like this. It's basically, it increases exponentially in a very simple language. So I think the positive side of that was clear. Now the negative is also clear, but there's some more things to note. So as x tends to negative infinity, let's see what happens to y. Because as x tends to negative infinity, obviously it gets we have a negative value, right? Because this x here is always going to be negative. But the thing about e to the x is that obviously e to the x has a property which is very important. And just to note here, so as the thing is that if x, tends to minus infinity, then e to the minus x tends to 0. So this is very crucial, right? Just you can just try this in the calculator just to get convinced. But the idea is that, because remember, e to the x is just 1 over e to the x, like this, right? And then just imagine, if you increase the x, then e to the x gets a very positive big value, and 1 over very huge value is just almost 0, right? So that's why as you increase x to minus infinity, e to the x tends to 0. So the reason I said that is very crucial here, because if we do so, sure, there are going to be some negative trajectory, but ultimately what's going to happen is that from the left hand side, e is going to tend to 0. So at some point we are going to indeed, have something like this. This is just, it's not a good sketch. Let me try again. So at some point, this is going to happen here. So like this, right? It's because it just, it happens because obviously we have a negative value, but as e to the x increases with the negative value of x, then the whole thing tends to 0 ultimately. Okay, now we are almost done, and I think for the rest of the graph you can kind of guess, but still we need to check some more things. So the next bit that I'm going to sketch is between these 2 points. So from the inflection point to the stationary point. Now the question is, how is going to be the direction? Is it, for example, going to be upwards? Is it going to be downwards? So that all comes down to the property and what happens between the inflection point and the stationary point. So the thing that we just need to remember was here. Remember that what happened here, we said when we add some small amount, some positive amount to -2, remember, is here. This is the point of inflection. And when we go to the right side of that, d squared y dx squared is positive, and positive second derivative indicates that this is convex, this part. And remember, a convex graph always has the form of this sort of U shape like this. So what it means for us is that from this part, the way that it's going to connect between these 2 points is like this, rather than going upwards like this, for example, because this would be the concave case, but it's not here, and that doesn't apply. So it's sort of like this. And remember that finally, this is the stationary point and it's a minimum. So hopefully this rings a bell, that if the graph is decreasing and then you suddenly get to the stationary point and it's a minimum, then it needs to shoot upwards after the minimum point. That's where the graph changes the direction and it gets connected. So the graph is not so accurate, but hopefully it's good enough to give you the idea that how this is going to work. Yeah, this is basically exponential increasing. Yeah. Okay, so that's it for this video, and thanks for watching.